Yeah, so in this talk I'm going to discuss the LAB and subduction zones from a seismological perspective. And let's see, the main motivation for this talk came from this figure, which I showed last summer at an imaging workshop. And of course, it was not to talk even mainly about subduction zone. It was mainly to put in context some of the imaging that I was doing and the imaging technique. But what happened is we ended up spending with the audience a lot more time than I expected on this figure, which was the first one. And the reason why we spent a lot of time is that many people asked me about where the LAB was, both on the subducted slab, although this is maybe clear, but especially here in the mantle wedge. And as you can see, indeed, like there's all the processes that you expect from a subduction zone, but there's not really an LAB that's indicated here. And then it got me thinking, and I thought about previous cartoons that I showed of subduction zones, and I noticed that a lot of them actually don't commit into showing where the LAB is. This is an earlier figure that I used to show in previous talks, which once again, you can see has a lot of information, really interesting information about subduction zone, all the processes that take place in here, temperature, where the megathrusts are, some of the hydration in these systems that we will talk about in a little bit. But again, it falls short of actually showing where the LAB is here. And even, those are two cartoons. Even when you go towards more quantitatively based models or cartoons or schematic, this is one by England and Katz from their Nature paper in 2010. Sorry, this bit cut from the side here. It's the same numerical model. Here is sort of a large version, and this is a zoom over this square here. Here there's a little bit more commitment. There's what appears to be an LAB right here, and an LAB down there as well. But these really are input parameters to these type of models. And if we follow some of the hypotheses that have been discussed until now and that you can see in the literature about what the LAB is, and here we can just pick one and say the LAB is a thermally controlled transition from rigid plate to viscous flowing mantle, in which case you can basically take one of the isotherms in these models and say, well, this is where the LAB would be. Here I picked the 1200, but I think a lot of people would say maybe, a lot of people who argue this would say maybe it's 1300 or a little bit more 1350. But then instead of having an LAB that's perfectly flat there, you would have an LAB that looks more something like this as you're approaching the trench. But this is again, so these are three cartoons that show subduction zones but don't really show the LAB or don't fully commit to it. But we can actually flip this around because we can image the LAB. And now let's look if in images of the LAB that have been published, we can see subduction zones. And here, I just took one example. It's from Lee et al. From the Potsdam group. They produced this really nice profile from A prime to A here, from about Baja California to about British Columbia, using some data from what I believe would be probably the first thumbprint of the TA array, so some of the first TA stations that were deployed as part of the EarthScope project. And again, this says LAB here. They show, and this is an SP receiver function profile, they show a really nice sort of feature discontinuity, negative discontinuity that they interpret as the LAB that you can see from south going to north. And then you go into this domain, JP, which is the Juan de Fuca plate. And there is a step here in that discontinuity, but other than that step, it's fairly continuous, and then they do continue this interpretation here. But one could assume that once you get in this region, you can see the profile going here comes very, very close to the trench of the Cascadia subduction zone, where the Juan de Fuca plate is subducting below North America. So presumably in here, there should be, the signal that we see here should not just be that of the LAB. There should be a component of LAB from the overriding plate, but there should also be a component from the subducted slab and from any of the processes that are happening in the mantle wedge. So what we're going to do in this talk is see how we can basically complement these studies and go to Smaller scale use more local high-resolution seismic imaging techniques to see how we can obtain some constraints on what the LAB may look like and how it may be affected by subduction zones and by the process of subduction. So this is a brief outline of what I'm going to be talking about. So seismic methods. Then we're going to look at the LAB of the subducted plate, the LAB of the overriding plate, and then how the LAB and mental flow, how does interruptions in the LAB or perturbations in the LAB and subduction zones may affect mental flow in the subduction system. So let's start with seismic methods. And I think we've had enough talks already today that I can show this and all of you know what this means. I know that there's not supposed to be any exams here at the Collège de France, but maybe we could pass a little piece of paper and you could say what do these different methods should tell us, and you should know already by now. But basically, there's two classes of methods that I'm going to talk about. The class of methods here that are on the left, they're based on diffracted and converted waves at rapid or sharp boundaries and material properties in the subsurface. A lot of you know receiver functions. If you have sort of stations that are quite sparsely spaced or even like fairly densely spaced, but when you get to really densely spaced station, instead of looking at sort of plane waves that are converting of plane boundaries, you can actually look at diffraction effect and migrate these scattered waves back to potential scatterers. Again, these two types of images give us some profiles, high resolution profiles of the subsurface with some ideas about sharp boundaries. And we are going to use also some shear wave splitting data or shear wave splitting measurements of SKS waves. And those provide us information about anisotropy in the subsurface and therefore as a proxy for fabric of minerals in the subsurface. And in a sense, proxy to mental flow in these environments. So let's first look at the LAB of the subducted slab. And to do this, I'm going to show an image that also has been showed several times today by Kawakatsu and co-workers for northeastern Japan and the Pacific plate. And what is shown here are some S receiver functions and P receiver functions from a borehole seismometers in the Pacific plate here that show fairly a clear negative pulse that corresponds to the LAB of the incoming Pacific plate that's about to subduct here below northern Japan. And here there's this spectacular profile that shows not only the oceanic moho, but below it the Lithosphere-Asthenosphere boundary that basically is following the moho and following the slab and plunges along with the slab at the trench. And that seems to be fairly continuous, at least in that portion of the system. So that's pretty clear. I'm not going to show other images. I think this one shows that we can pretty clearly say that this is the behavior of the LAB from the standpoint of the subducted slab. And we'll come back later to see how this affects mental wedge, sort of mental flow. We'll see that actually the mental flow is being affected definitely by this plunging slab, as one would expect. So let's move on then to the LAB of the overriding plate, and where it's bound to be more complicated because there's some fluids that are fluxed into the mental wedge. There's some corner flow in there, and so it might not be as clear. And so before we look at some seismic images, let's look at where the overriding LAB is expected to appear. And again, before looking at seismic images, we're going to look at some cartoons and see what we would expect or where we would expect the LAB to appear. So we go back to this cartoon that we showed at the beginning. This is our subducted slab. This is our overriding plate here for our crust. And of course, we want to start to look for an LAB where the overriding plate starts. And where does it start? It starts pretty much at the trench. I mean, there's the accretionary prism there, so you can say it can start a bit later, but let's start it here for now. The issue here is that, of course, we have subducted crust in contact with overriding crust, right? So it's crust on crust. It's often called the megathrust. That's where megathrust earthquakes happen. So crust on crust, there's obviously no LAB there to be found. So we have to move further inland. As we move further inland, the subduction interface encounters the cold portion, sometimes called the cold nose, of the mantle wedge. And in this cold nose, the temperature limits corner flow in that part of the mantle wedge, and also the temperatures of the mantle wedge are cold enough that the minerals, the peridotites, the mantle rocks of the mantle wedge will take in some of the fluids that are fluxed by the slab and become hydrated. And this is, then those minerals do transform into serpentine. And that can happen over this whole portion, and if it does happen over this whole portion, then again, you wouldn't have any LAB here. I labeled this, you know, the lab killer, because I thought it was funny, but maybe it's a bit exaggerated, because maybe there's no LAB to kill there in the first place anyways, right? Since you are really in a portion that is not circulating, both because of the temperature and because you have serpentine that is fairly buoyant. Maybe a better lab killer would be the plume that, or the whatever material Kate was showing below the FR. Now that's a plate killer, an LAB killer. So presumably, we would expect the LAB to start somewhere from this point onward. And onward, I mean landward. And where this point is, of course, will vary from one subduction to another because you have different thermal regimes. So that nose and that corner of the subduction zone might be colder in some areas, warmer in other areas. It might have serpentine in some areas and not in other areas. So let's go to seismic images then. And can seismic images help us then at least define or have an idea of where that LAB may start? And for this, I'm going to go back to some work that we've done more than 10 years ago now with doing some seismic images in the Cascadia subduction zone. So what you see here at the top is a thermal model of the Cascadia subduction zone across central Oregon. And the image, the profile that you see below, that's a seismic migration profile. And just to give you an idea, what you see here, as you know, it's indicated here, but again, red colors indicate lower velocities, blue color, faster velocities, and we see two main features in there, or two robust features. One of them is a dipping low velocity layer that corresponds to the hydrated oceanic crust that's being subducted. We lose some of this signal at around 40 kilometers depth, which is where we expect eclogitization to happen, which brings up the seismic velocities and therefore makes this crust less observable, or its signature lower. And here to the right, you see the continental moho that goes from lower velocities to faster velocities below. Above here, again, as I said, is a thermal model of this subduction zone. And the square box that you see here is the part where the temperatures are expected to be low enough such that serpentine can exist. They're maybe a little bit too high. I mean, this actually comes and meets the 800 degrees. Serpentine is actually stable to lower temperatures than that. I mean, more of the order of 600 degrees. So that box should be a little bit smaller. But what's interesting is when you look at this image here, what you see is if you follow the moho towards the subducted slab, you see a fairly strong signal, and suddenly around here, it starts to diminish, it starts to disappear. And then eventually it even flips polarity. And this was interpreted in a paper that Michael Bostock and co-authors wrote in 2002 as the serpentinized portion of the mantle wedge here. And why do we not see it anymore? Because serpentine tends to lower the seismic velocities. 5 minutes, wow, okay. I'm gonna start to accelerate here. So presumably this would tell us that this is where the LAB starts. Now let's look at, since this profile, we've generated 3 different profiles in the Cascadia subduction zone. All of these show similar features, and you can see here that all of them seem to show a serpentinized portion of the mantle wedge. So the LAB would start after this. Now, do we see the LAB after this in Cascadia. Well, again, before we look at the images, let's look again at what models would tell us. And what a lot of thermal models have told us in recent years, and this is a cartoon based on thermal models, is that if you have temperature-dependent viscosity in your models, there's an important upward component of mental flow in your mental wedge, which causes a thinning of the lithosphere by thermomechanical erosion. And so you have both the isotherms and the lithosphere-asthenosphere boundary that would be expected to thin in that region, and therefore you have melt then that's being generated in there, and it's probably being focused thanks to what's called here this pinch zone, this thinner zone, by melt accumulation below, and then that produces the arcs that are fairly linear at the surface. So if we go to our images, do we see some features like this? Well, it's tempting, though, here to say, well, you know, we have this moho going from slow to fast velocities, and then we fall back into low velocities again. But we did some tests on this, and there's no way for us of really seeing whether this is a real feature or a side lobe of the receiver functions. And in any case here, that signal would be fairly low. So in Cascadia, it's probably not observed very well. But there's one place where we believe we observed it very strongly, and that's in the Alaska subduction zone, at the eastern terminus of the Alaska subduction zone below Anchorage in Fairbanks, where you have sort of flat subduction of the Pacific plate in that region. Not exactly flat, but very low angle. And what's happening in that case is that you actually have advancing subduction, right? The opposite of rollback. So you have cooling of this whole system. You have very limited volcanism in this region, and when you look at the profiles similar profiles to the one in Cascadia that we've obtained here, you again have your low velocity layer over here, you have your moho that is observed here, and you have this really strong sort of fast to slow boundary that we see here, and it's sort of indicated here. And with the way we interpreted this with Laurent Montesi, we built some thermal models to try to explain this, and we found that by accommodating or taking into account sort of the advancing subduction zone, you're cooling off the system, you're flattening the LAB, because you don't produce as much of a pinch zone. Melt might be rising and has more of a tendency to then pool at the base of the LAB in that case, because you have cooler system, maybe less melt being generated, and less focusing of the melt near a pinch zone that is inexistent or non-existent in that case. And therefore, you have ponding of melt below these layers, which could be a sort of LAB. So LAB can be observed maybe in subduction zone, but more when it is illuminated by partial melt. And let's see. Do I still have a few minutes? Yes? Okay. Oh, okay. I was told, so I suddenly accelerated. Let's go back. No, I was told suddenly 5 minutes. And so if you heard me accelerate, it's because I was just thinking, oh my gosh, I have to get through all this still. Okay, so now I can breathe. Excellent. I'm going to drink water. Okay, so now let's look at the he's a good chair, isn't he? So I'm going to be able to show everything. So now let's look at the LAB. So now that we've looked at structure of the LAB, both on the incoming slab, but also in the mental wedge, or that is in the overriding plate. Now I hope I give you a few constraints on this. Let's see how this can affect mental flow, and if we can have any information about mental flow in this system. And again, as I said at the beginning, a good proxy for mental flow is to measure seismic anisotropy. So, and here I'm going to show some SKS measurements that we made in the Hellenic subduction zone across two very dense arrays that we deployed in southern Greece and then in northern Greece in an experiment that was called the Medusa experiment that ran from 2006 to 2009. And so again, SKS splitting gives good information about fabric and the mental sort of lightest preferred orientation or shape preferred orientation, and can be a proxy for mental flow. So before I talk about these results, I want to say that there's been some amazing compilations of shear wave splitting results that have been made in the last few years that have shown how shear wave splitting varies from one subduction zone to another. And so, of course, one of the things that shear wave splitting gives, as we saw in previous talk, is the direction of polarization, or of fast polarization of S waves. And so in these compilations that have appeared in recent years, people have tended to categorize subduction zones as either being dominantly trench parallel polarization or trench perpendicular polarization. But here, when we look at the Hellenic subduction zone, we actually find three different domains of splitting. And these are, we refer to them here in green as the near trench domain, then in blue as the forearc domain, and in red as the back arc domain. And when you're very close to the trench, you have this near trench domain, and you see dominantly trench perpendicular anisotropy. Then you rapidly change, or it rapidly varies to the forearc domain, which is trench parallel, and then in the back arc, you switch back to a trench perpendicular one. So we see three different domains with the two different types of anisotropy there. Maybe one of the reasons why we see this is because we have really dense arrays in this region. Which means that here, if the Hellenic subduction zone could speak, it would say this. That's roughly translated from the Greek. It would say, don't categorize me. I'm neither just a trench parallel nor a trench normal anisotropy subduction zone. I am much more complex and intriguing. And then it would say, I'm much more than the sum of my parts, etc. But, you know, but that's what is happening there. And I think that this is something that should be considered when looking at subduction zone, is to try to, when you have the high resolution, to notice that it's actually possible, perhaps in many cases, to see these different domains of anisotropy. And that's been seen in other subduction zones as well, when you have dense arrays like this. What becomes really cool is when you take these measurements of shear wave splitting and look at them in conjunction with a high-resolution imaging profile like the ones I've shown until now for Cascadia and for Alaska. This one is a little bit washed off, so I'm sorry about this. But this is for northern Greece. We see subduction crust here, subducted crust. Notice it's continental crust. I won't go into the details of this, but there in northern Greece you have continental crust subducting as opposed to oceanic crust. But we see the same thing happening both in northern Greece and in southern Greece. And what happens here is that you go from the near trench domain, which is trench perpendicular, and look at this. You basically switch by 90 degrees almost your fast axis of polarization exactly at the point, almost exactly at the point where your subducted slab encounters the overriding moho. And then suddenly, boom, you just jump by 90 degrees, and then you get into this forearc domain, which is trench parallel. And then after that, somewhere in the back arc, you switch back to trench perpendicular. So the idea here is that there is, and we analyzed this data to try to figure out where that anisotropy came from. That's not a unique type of modeling, but we found out that by comparing with other studies that the anisotropy here was most likely related to sub-slab flow. And, but obviously here, as soon as you meet the moho, what must be happening is that the mantle wedge starts to dominate your signal of shear wave splitting that you see at the surface. And then here, again, this is probably related to the asthenosphere. So we've tried to come up with a model to try to explain this. And the way we can explain this here is that the anisotropy that we see, the trench perpendicular principal axis of anisotropy that we see in the near trench is probably due to asthenospheric flow below the subducted slab. In this case, the slab is retreating, and there's a number of models in recent years that have come out that do suggest that even for retreating slabs, you do have a small layer of trench perpendicular fast or main axis of strain, which would correspond to the fast axis. That is, if you assume a viscous coupling between the asthenosphere and the subducted slab. Here, in what would be the back arc, you again have a mantle flow that is dominated, or an anisotropy that is dominated by corner flow, mantle flow in your system, which causes fast axis to be poloidal. That, of course, is as long as you're away from the edges of your subducted slab. And here, in this part of the wedge, where you have trench parallel anisotropy, you probably have an anisotropy that's being dominated by processes that occur in that cold part of the mantle wedge. So either it could be serpentinite. Serpentine has been shown in recent years to be able to cause trench parallel anisotropy. It could also be caused by B fabric, which is a sort of when hydrated materials in that part of the wedge are at cold temperature and under high stress. Here in Greece, it's unlikely to be created by what people refer to as toroidal flow, which has been invoked to explain some of the trench parallel flow in some subduction zone, because you kind of have to be relatively close to the edge of your subduction zone or the edge of the slab to see some of the signal. Here, I mean, in the north we might be close enough, but in the south we're definitely several hundreds of kilometers away from it, and so it's more likely to be something that is of mineral origin in the mantle wedge. This is here a plain view of this subduction, of this profile that's right here. So I'm going to be able to finish on time then. So here are some concluding remarks. I hope that I was able to show you that the LAB and the underlying mantle flow are laterally, I mean, this is something that we expect not just from the seismic images, but they are laterally discontinuous as subduction zones. And the local high-resolution seismic images that we've shown here give us a glimpse of how the LAB system behaves in these regions. The LAB of the subducted slab is well defined, but it dips with the rest of the slab beyond the trench. The LAB of the overriding plate effectively starts past the cold and potentially serpentinized portion of the mantle wedge. And the LAB of the overriding plate is not necessarily, at least with our images, is not necessarily well imaged everywhere, but it seems to be well imaged, especially in cases of advancing slabs where you have cooler mantle wedges that might cause some of the melt and some of the fluids to pond and thus illuminate the lithosphere-asthenosphere boundary. But sort of as an outlook comment here, we obviously still need to establish a link between long-range LAB profiles, such as the SP receiver function profiles that I showed at the beginning, and that combine these with local and regional imaging approaches. That's seismic, but of course we also have to combine this with other methodologies, as was said in previous talks. So we have to combine different scales of seismology and then seismology with other methods. All right, thank you.